Imagine the universe when it was just a fraction of a second old. It was an incredibly hot, dense soup of energy and exotic particles. Everything was a blur. There were no atoms, no stars, no galaxies, just a seething, uniform plasma. As the universe expanded, it cooled down, and when things cool down, they change. Think about water. When you cool water, it eventually freezes and turns into ice. This is called a phase transition. The universe went through phase transitions just like that, but on a much grander scale. A cosmic string is a theoretical idea. It's a proposed leftover from one of those early phase transitions. It's like a crack that formed in the ice as the water froze. But instead of a crack in ice, it's a crack, or a wrinkle, in the very fabric of space-time itself. These aren't strings like the kind you tie a box with. They are lines of pure, trapped energy from that very early, very hot state of the universe. They are fossils from the first moments of creation. Let's stick with the freezing water analogy because it's really helpful. Imagine a huge lake freezing over on a very cold day. Ice crystals start to form in different places all at once. The crystals in one spot might be oriented in one direction. The crystals a mile away might be oriented in a completely different direction. As the ice spreads, these different regions eventually meet. Where they meet, they don't line up perfectly. You get a long, messy line or a jagged boundary between the different crystal domains. A cosmic string is basically that boundary line, but for the entire universe. In the early universe, as it cooled, a fundamental field that permeates all of space had to choose a state to settle into, much like water has to choose how to orient its crystals when it freezes. In one vast region of space, the field might have settled into one state. In another region, it might have settled into a different but equally valid state. Cosmic strings are the defects, the thin lines of leftover high-energy confusion that got trapped at the boundaries where these different regions of the universe met. They are one-dimensional mistakes in the cosmic freezing process. So what are these things actually like? Their properties are pretty mind-boggling. First, they are unbelievably thin. We're talking thinner than the nucleus of an atom. If you scaled up a single atom to be the size of our solar system, a cosmic string running through it would still be too thin to see. It would be thinner than a single human hair in that massive solar system-sized atom. But even though they are thin, they are immensely massive. A cosmic string is a concentration of the energy density of the early universe. This makes them incredibly dense. A single inch of cosmic string could weigh more than a mountain. Some calculations suggest a piece the length of your car could have more mass than the entire Earth. This isn't mass in the way we think of a rock having mass, it's mass energy, as described by Einstein's EMC raised to the power of 2. They are pure, raw energy woven into a one-dimensional line. Because of this incredible mass, they are also under colossal tension. Think of the most stretched rubber band you can imagine, then multiply that tension by a factor of trillions upon trillions. This tension is the defining feature of a cosmic string. It pulls on the string, always trying to make it straighten out. If a string has any wiggles or kinks in it, this tension will try to smooth them out, making the wiggles travel down the string like a wave on a whip. This enormous tension is what makes cosmic strings so dynamic. It causes them to whip around through space at speeds approaching the speed of light. And these strings would be long, very long. Some could be infinite, stretching across the entire observable universe. Others could form closed loops, perhaps the size of a galaxy or as small as a planet. An infinite string would just keep going, while a loop would be trapped, oscillating wildly under its own tension. So you have these impossibly thin, incredibly heavy, universe-spanning defects whipping around at near light speed. If they exist, they should have left some fingerprints on the cosmos. They aren't just a quirky theoretical idea, they would have real observable consequences. The search for these consequences is how scientists are trying to figure out if cosmic strings are real or just a fascinating mathematical possibility. One of the biggest effects a cosmic string would have is on light. According to Einstein's theory of general relativity, mass and energy warp the fabric of spacetime. Anything with mass, like a star or a galaxy, creates a sort of dip in spacetime, and light follows these curves. This is called gravitational lensing. A massive galaxy can act like a lens, bending the light from a more distant object behind it, making it appear distorted or magnified. A cosmic string would also act as a gravitational lens, but in a very specific and strange way. Because a string is a line, it doesn't create a dip in spacetime like a star does. Instead, it sort of pinches it. The geometry of space around a cosmic string is flat. It's normal, but the string itself represents a deficit. Imagine taking a flat piece of paper, cutting out a thin wedge-shaped slice, and then taping the two cut edges together. You've created a cone. The surface of the cone is still flat. You can lay a ruler on it and it will lie flat. But the overall geometry is weird. To get from one side of the seam to the other, you have to go around the point of the cone. A cosmic string does something similar to spacetime. It removes a small wedge. Spacetime is flat everywhere, but there's this line where a piece is missing. So what happens to light from a distant galaxy that passes by the string on its way to Earth? If the string is between us and the galaxy, light that goes to the left of the string will travel along its normal path. As light that goes to the right S string of the string will also travel along its normal path. But because of that missing wedge of spacetime, those two paths will bring the light to us from slightly different directions. The result is that we would see two identical images of the same galaxy right next to each other. Not distorted or magnified like in normal gravitational lensing, just a perfect duplicate. It would be like looking at a single candle and seeing two identical, undistorted flames side by side. Finding a pair of identical galaxies or quasars like this would be a smoking gun for a cosmic string. Astronomers have spent decades searching for such a signature in maps of the sky. They have found a few candidate pairs that looked promising at first, but upon closer inspection, they turned out to be two separate but very similar galaxies or a lensing effect caused by a more conventional massive object. So far, no confirmed detection. Another major way we could find cosmic strings is by listening for their sound. Not sound in the air, but gravitational waves. Gravitational waves are ripples in space-time itself, created by the acceleration of massive objects. We've detected them from merging black holes and neutron stars. Cosmic strings, if they exist, should be fantastic sources of gravitational waves. Remember how they are under immense tension and whip around at near the speed of light. When a string has a kink, that kink will travel down the string and can slam into another kink, creating a powerful burst of gravitational waves. More importantly, when two long strings cross each other, they can trade partners and reconnect, creating a closed loop. A cosmic string loop is an unstable thing. It will oscillate wildly, radiating away its energy in the form of gravitational waves. As it loses energy, it shrinks, oscillating faster and faster, until it eventually radiates all its energy away and vanishes in a final burst. This process, happening all over the universe since the beginning of time, would create a constant hum of gravitational waves. It's called a stochastic gravitational wave background. It would be like the background hiss you hear on a radio that isn't tuned to a station. Our current gravitational wave detectors like LIGO and Virgo are best at hearing the loud short chirps of black hole mergers. They aren't as good at hearing a faint, constant background hum, but other experiments, called pulsar timing arrays, are designed to do just that. Pulsars are incredibly dense, spinning neutron stars that send out beams of radio waves like a cosmic lighthouse. They are unbelievably precise clocks. A pulsar timing array uses a whole network of these pulsars across the sky. By timing the arrival of their pulses with extreme precision, we can detect tiny disturbances in the space-time between us and the pulsar. A passing gravitational wave would stretch and squeeze space-time, causing the pulse to arrive a tiny bit early or a tiny bit late. If we see a correlated pattern of these delays across all the pulsars in our network, it could be the sign of a stochastic background of gravitational waves. Scientists are actively listening for this hum right now. A detection would be huge news, and one of the possible sources could be a network of cosmic strings. There's another place we can look for evidence, the very first light in the universe. This is the cosmic microwave background, or CMB. It's the afterglow of the Big Bang, a faint radiation that fills all of space. It's an almost perfectly uniform temperature, but it has tiny, minuscule variations. These tiny hot and cold spots were the seeds that eventually grew into all the galaxies and clusters of galaxies we see today. The leading theory for where these seeds came from is called cosmic inflation, a period of hyperfast expansion right after the Big Bang. Inflation would have stretched tiny quantum fluctuations into a specific pattern of temperature variations in the CMB, and the patterns we've observed with satellites like WMAP and Planck match the predictions of inflation incredibly well. However, if cosmic strings were present in the early universe, they would have also left their mark on the CMB. A moving string would create a wake in the primordial plasma, sort of like a boat moving through water. This wake would leave a sharp, linear discontinuity in the temperature of the CMB. It would look like a sudden temperature jump along a line. Scientists have meticulously scanned the CMB maps for these specific line-like features. They haven't found any clear, unambiguous evidence. The lack of these signatures is one of the biggest constraints on cosmic string theories. It doesn't mean strings don't exist, but it does mean that if they do, they can't be too massive or too numerous. They must have played a smaller role in shaping the universe's structure than inflation did. This actually brings up an interesting part of the history of the idea. In the 1980s, before we had such good data on the CMB, cosmic strings were a leading competitor to inflation. The theory was that the gravitational pull of a network of strings could have been what pulled matter together to form the first galaxies. The strings would act as gravitational seeds. It was a beautiful and compelling idea. But when the precise CMB maps came in, they showed a pattern of fluctuations that was a much better fit for the predictions of inflation. So, the idea of strings as the primary seed for cosmic structure fell out of favor. But that didn't mean strings couldn't exist. They could still be out there as a more subtle component of the universe. What would happen if a cosmic string passed through something? This is a fun thought experiment. What if one passed through the Earth, or you? It sounds catastrophic, but it might be surprisingly gentle. Remember, the string is subatomically thin. It's not like a physical wire that would bulldoze through matter. It's a line of warped spacetime. As it passed through you, the particles in your body wouldn't really hit it. They would just experience the strange geometry of spacetime around it. For a brief moment, space would be conical, right where the string was. The main effect might be a quick gravitational jolt. You probably wouldn't be sliced in half. In fact, you probably wouldn't notice a thing. The gravitational effects are strong, but the interaction is over in a fraction of a second as the string passes by at nearly the speed of light. Passing through a star would be more dramatic. The string's intense gravity could trigger instabilities or turbulence within the star's plasma. But again, it would pass through so quickly that it might not cause the star to explode. The more likely scenario is that the string would barely notice the star was there, and the star would be left with a temporary, rapidly fading scar. The real danger isn't being cut, it's the sheer gravitational energy. A small, oscillating loop of cosmic string decaying nearby could release a burst of energy and high-frequency gravitational waves that would be very destructive. But a long, straight string just passing through is more of a cosmic curiosity than a doomsday weapon. It's also important to understand where cosmic strings fit into the bigger picture of theoretical physics. They are a type of topological defect. This is a general term for stable, leftover structures that can be formed during a phase transition. Depending on the exact physics of the phase transition, you can get different kinds of defects. If the defect is a single point, it's called a magnetic monopole. This is a hypothetical particle that would be like a magnet with only a north pole or only a south pole. We've never found one. If the defect is a two-dimensional sheet, it's called a domain wall. A domain wall would be a giant wall of energy stretching across the universe. These would be a big problem because a single large domain wall would contain so much mass that it would dominate the gravity of the entire universe, which is not what we observe. Cosmic strings are one-dimensional defects. They are, in many ways, the most plausible of the bunch. They are massive enough to have interesting effects, but not so massive that they would have already ruined the universe as we know it. This makes them a sweet spot for theorists and observational astronomers. The story of cosmic strings also connects to one of the biggest ideas in modern physics, string theory. This can be a bit confusing. String theory proposes that the fundamental constituents of matter, electrons, quarks, and so on are not point-like particles, but tiny, one-dimensional vibrating strings of energy. These are the fundamental strings, and they are incredibly small, existing on a subatomic scale. A cosmic string is a totally different beast. It is a macroscopic, or even astronomical, object. It's a defect in spacetime, not a fundamental particle. However, some versions of modern string theory, especially those that involve extra dimensions of space, actually predict that in the early universe, some of those fundamental tiny strings could have been stretched to cosmic sizes during the period of inflation. These objects, sometimes called superstrings, would behave a lot like the classic cosmic strings. So the search for cosmic strings is also, in a way, a search for evidence that could support the broader framework of string theory. Finding a cosmic string would be a monumental discovery, not just for cosmology, but for our most fundamental understanding of reality. So where do we stand today? Do cosmic strings exist? The honest answer is we don't know. We have some strong reasons to believe they could exist. They are a very natural consequence of many well-regarded theories in particle physics about how the universe works at high energies. The mechanism that creates them, a symmetry-breaking phase transition, is a standard part of our understanding of physics. It would almost be more surprising if the universe went through such a transition and didn't produce any defects at all. However, we have no direct evidence. The searches for their gravitational lensing signature have come up empty. The searches for their signature in the cosmic microwave background have also come up empty. This has ruled out many of the simplest and most massive cosmic string models, but the game isn't over. The hunt has shifted to gravitational waves. The new generation of experiments, especially the pulsar timing arrays, are just now reaching the sensitivity required to detect the faint background hum that a network of cosmic strings might produce. There have been some tantalizing hints in the recent data of a background signal, but it's still too early to say what is causing it. It could be cosmic strings, or it could be something more mundane, like the combined signal from countless supermassive black hole mergers across the universe. We need more data to tell the difference. Even if we never find one, the idea of cosmic strings has been incredibly useful for physics. It has forced us to think hard about the connection between the very small particle physics and the very large cosmology. It has pushed our observational techniques to their limits and led to new ways of analyzing data from telescopes and gravitational wave detectors. It's a perfect example of how a beautiful theoretical idea can drive scientific progress, even if the idea itself turns out not to describe our reality. In the end, a cosmic string is a magnificent possibility. It's a remnant of the universe's violent birth, a thin, dense filament of pure creation stretching across the eons and across the vastness of space. It's a wrinkle in time, a scar from when the universe changed its mind. Finding one would be like finding a bone from the first living creature. It would give us a direct physical link to the first fraction of a second of the Big Bang, a time and energy scale that we can never hope to recreate in our labs on Earth. And that is why the search continues. Out there in the dark, astronomers keep looking for that telltale double image and listening for that faint cosmic hum, hoping to catch a glimpse of a fossil from the dawn of time.